So now we understand a little bit about reaction rates. Let's take a look at something called the rate law. Now, in order to understand the rate law, we have to understand a little bit more about what's going on here. And this is a way of representing reaction rates. We know that reaction rates change as a reaction occurs. It's not a constant sort of thing. What's also interesting is that most reactions, once you've got a certain amount of product, and those product molecules are circulating and encountering each other, sometimes reactants can go back and form, or products can go back and form reactants again. That means that reactions are reversible. Almost all reactions are reversible. It's just that if the rate is fast enough and if we produce a tremendous amount of product, often we miss the reversibility. We'll deal with all of this stuff when we talk about equilibrium, because that deals with reversible reactions. But because reactions can reverse, that complicates things when we're talking about the rates, because you've got competing rates then. You've got the rate of product formation, but then some of the products are reacting together to form reactants again, and so you have a very strange and complicated situation. So to avoid that, we deal with instantaneous rates right after the reaction starts, like where the rate is the fastest, usually. Because, well, for one thing, it's most easily measurable right after reactions start. We can know what our initial reactant concentrations are, and at some point we can try to measure reaction concentrations of both reactants and products as we go. So that happens best when the rate is fastest and our concentrations are fairly high of reactants. But it also prevents us from getting to the point where the products start to react with each other and form reactants again. The reversibility becomes an issue. So we can ignore it if we look at instantaneous rates at the beginning. Okay, so that means that if we're doing that, and if we're evaluating reaction rates by looking at early rates, then that means that the rate of a reaction, how fast it occurs, really only depends on the concentration of reactants. Now, there are some other factors that affect reaction rates and things that should make sense. The physical state of a substance, for example, is a liquid or gas. How well can the reactants mix with one another? Gases mix together really well, so gas reactions generally tend to be very fast. Liquids, well, you've got some movement of particles, and they might be able to sneak in there and get in touch with each other and react. Allotropes. An allotrope is a different form of the same element. For example, carbon has several allotropes: diamond, graphite, Buckminster fullerene, nanotubes, graphene. All of these are different arrangements of carbon atoms in solid form. Well, diamond reacts differently than graphite does. There's a different type of reaction there, and that has something to do with the way that the atoms are connected. sp3 hybridization for diamond or sp2 hybridization for graphite. You get different reactions. Is it a solid versus aqueous? If you put two solid ionic compounds together, they will take a long time to react because the ions just can't get at each other if they're stuck in a solid crystal. But if you dissolve them and separate the ions, you might get a faster reaction that way. How reactive are the elements involved? Sodium is much more reactive than calcium, so sodium compounds are going to react probably a little bit faster than calcium particles. And then overall particle size. The smaller the particle size, the greater its surface area. The greater its surface area, the faster the reaction generally will go. So one of the ways that we can represent the rate of a reaction is by using something called a rate law. Okay? The rate law is an expression, mathematical expression, and it shows the relationship between the concentration of the reactants and how fast the reaction is going. That's what a rate law is. It's sometimes called differential rate law, but that's what it does. Okay, an example for our reaction of NO2 to NO plus O2 that we had in a previous video. The rate law would be written as follows. Rate equals K times concentration NO2 to some exponent N. K is something called proportionality constant, or the rate constant. And for each reaction under certain conditions, K will be constant. It will have a value that you can either calculate based on data or that you can actually use in a calculation. N, the exponent, is something called the order of that reactant. Okay? It is something that must be determined experimentally You can't just look at an equation for a reaction and figure out what N is usually. There are a couple of very specific situations where that might be possible, but usually the only way to determine the N value of N is to do an experiment, several experiments, and look at how the rates change. Okay? Typically, N is a positive integer. It may be fractional. Unusual reactions have fractional orders. It could be 0. And you know that anything raised to the 0 power is just 1. So if that is 0, then the rate is considered to be 1, whatever that means. So we'll understand that in a bit. Okay? So that's what the rate law looks like. All right? We can use the rate law to determine some things about a reaction. Okay? To determine some information about what's going to happen in terms of how it's going to react. So here's some examples of how the rate law can describe or help us to understand a reaction, or how we would write them and what they would mean. For example, we have 3NO, nitrogen monoxide gas, and that can react with itself to form N2O, dinitrogen monoxide gas, and NO2 gas. Okay? The rate law for this might look like this. Rate is equal to, again, proportionality constant K times concentration of NO to the second power. Again, this 2 has to be determined experimentally. You can't just look at this equation. Where's a 2 in here that would fit up here? It doesn't really make any sense. It will once you start learning how the experiments can prove that. Okay, but what this 2 means is that this reaction is second order in NO, the reactant NO. And that's what that means, that this concentration of NO, the reactant NO is in second order somehow, whatever that means. We'll see that in a second. The other thing we can tell if this is the entire rate law is that this reaction is second order overall. And the way you determine the overall order of a reaction is by adding up the exponents in your rate law. Okay? Let's take a look at another one. Let's do 2NO2 gas plus F2 gas, fluorine, producing 2NO2F gas. Okay? The rate law for this reaction is K times concentration NO2 times concentration F2. All right? So my exponent for NO2 is a 1 and my exponent for F2 is a 1. I don't have to write them in there if they're 1s. Well, what does this mean? What information can we get? Well, we say that it's first order in NO2 and it's first order in F2. And that means that it's second order. We add up these two. That means that this reaction is second order overall. Okay? So what does the order mean? Like, what's the definition of order, or how does it work? Well, I'll give you an example. Here's a hypothetical reaction. A plus B plus C forming some sort of products. And again, because we don't really care about the products, we care about the nature of the reactants. Okay? The rate law for this reaction might be rate is equal to K times concentration A times concentration B squared. Okay? So that's my reaction rate. What that means is that it's first order in A. Okay? It's second order in B, and technically, let's make this a different color just so that we don't get too confused here. Technically, this is zero order in C, right? So it's zero order in C. Because that's a 0, this whole term is a 1, so we don't generally have to write it in there. All right, well, what does this mean, first order in A, second order in B, zero order in C? Remember, the rate of a reaction depends on the concentration of reactants. So if I were to do this reaction, I would measure a rate. I would figure out how fast A is decreasing, B is decreasing, C is decreasing. Okay, and then I could do the reaction again and change the concentrations of A or B or C. I'm going to change only one of them to see what happens to the rate. Okay, in the case of A, if I leave the concentration of B and C alone, but I double the concentration of A, because A is first order, if I double this concentration term in the middle here, if I double A, then the rate is going to double. Okay? So if this was 2 and this was 1, and this doesn't matter what this is because it's going to be 1 anyway. If this is 2 times 1, 1 squared, which is 1. 2 times 1 squared is 2. The rate is 2, right? If I double this to 4, and I leave this alone and I leave this alone, 4 times 1 squared is 4. The rate doubles. Now, what if I leave the concentrations of A and C alone, but I double B? Well, because this is squared, if I leave A and C alone, but I double B, the rate will double and then square will both be 4 times. So again, if this is 1, or if this is 2 and this is 1, the rate is 2. If this is 2 and this is now 2, the rate is 2 times 4, or 8. We've quadrupled the rate by doubling just the concentration of B. If I double C and don't change A and B, nothing happens, because whatever the concentration of C is, it's to the 0 power. It means this always becomes 1 and nothing changes. Okay? So that's how the order of each reactant affects the rate. Now the question is, what happens if I do this reaction, I measure the rate, and then I do it again and I double A, B, and C? How much does the rate change? Did you figure it out? It's 8 times. 8 times as much. It doesn't matter if C doubles or not. That doesn't affect the rate because it's 0 order in C. If I double A and B, then it becomes twice and 4 times faster, which is 8 times faster. So it makes it 8 times faster than it originally was. So the rate law has to specify the reactant it's referring to. And sometimes it'll just be one reactant, sometimes it'll be many reactants, or all of them sometimes, okay? The rate of the reaction depends on what reactant or product the rate law is defined in terms of, right? The value of the rate constant depends on how we define the rate as well. It also depends on certain conditions of the reaction. Okay, so there are a couple of different types of rate law. There's the differential rate law that we talked about. This is the kind we've been talking about. It's just sometimes called the rate law. And it shows how rate and concentration are related, how the concentration of reactants affects the rate. There is something called the integrated rate law that we'll see a little bit later on, and that shows the relationship between concentration and time. Now, these are two different things, and I want you to make sure you understand the difference between them. The rate is how fast a reaction happens. The time is how long it takes for that reaction to occur. They are similar and related, but not the same thing. Okay? Now, each of the rate laws will have a specific integrated rate law that goes with it, and we'll take a look at some of the most common ones in another video. Okay, so make sure that you go back and understand the relationships between the rate law and the concentrations of reactants and how that all works, especially how orders work.